This is about this is about still memory management, but the two techniques to avoid external fragmentation, which is segmentation and paging. So this part 2 is going to discuss segmentation and paging. First, we will start with segmentation. When you see segmentation, basically, this one is objective. It's talking about. So let's talk about segmentation. This is a way of avoiding external fragmentation. So remember that whenever you discuss about your program, basically why we come for the segmentation is we have the user process to be assigned to the main memory, allocated to the main memory. When you're thinking about a user process, let's say a program, you will have this kind of areas in your program, like your main program, and it has some methods, procedures, or functions, whatever is it. And you may also have some arrays, like kind of data structures, array stacks, or some variables in it. So basically your program contains certain modules and some data. Okay then. So each module and your data may contain some name. It all referred by a name. Name of your method, name of your function, name of the variable. Okay. And when you have the stack, I mean to say the libraries or whatever is it, and then it may occupy some locations, and that locations may have some addresses. You get the idea? So this is a general idea. What do you think about your program contains some segments? It may have some modules. You call module in a programmer way. You call it modules. Module means a method or part of your program. So that is the way we are going to discuss here segments. Okay. So when you talk about segments, you see a programmer prefer to see memory as a collection of variable sized segments. Okay, segment means this is the hint I gave you in the previous slide. When you think of your program contains various modules. So that is the thing. Modules means segments of your program. So that is the thing. Your memory is considered as a collection of segments. Okay. So you just see the segment is of variable sized segment, not all of same size. Okay, maybe one segment is bigger than the other segments. So how are you going to access the segment, and how are you going to access a location in your segment? So that will be by segment name with offset. Every segment will have a name, and each segment will have certain locations. Okay, so I'm going to have offset. Offset will enable me to access a particular location in a segment. Okay, that we will see in the upcoming slides. So basically we need to have a segment name and offset. So if you have these two, you can easily access a location inside a segment. Okay. So segmentation is memory management scheme, segmentation and paging. Now I start with segmentation. That supports programmer view of the memory. You view your memory as segments. Okay. Logical address space is a collection of segments. Remember, your logical address space is a collection of segments. Okay. Each segment has a name and a length. Okay, every segment has a name. The addresses specify both the segment name and the offset within the segment. Remember, the offset has to be with segment. So you have to specify the address. The address contains two parts. What are the two parts? Segment name with the offset. Okay. So your address, let's say if you are talking about an address contains the segment name comma, offset, the two things. Okay, then the segments are numbered, like segment name. I told you that you need to have a segment name and the offset. So the name of the segment is going to be the number, like segment 1, segment 2, segment 3. So the segments are numbered for simplicity, for easy understanding. Okay, and are referred to by the segment. Okay, if you're going to refer the first segment, it's going to be segment 0. So you start with 0, something like that. So if I say segment name, name is hard to understand. So let's say the number. Like every one of us, we have a student number. Is it? A student name, student number. So easy thing is student number. Okay, then because there may be many students with the same name, it's not going to be unique. So let's have a number, segment number. So logical address contains two things, which is the segment number, comma, offset. Okay, when you are compiling the program, compiler automatically construct the segments reflecting the input program. So it automatically construct the segments. Fine. So we need to have a number plus the offset so that you can able to easily access the segment. Fine. So let's assume a C compiler. So C compiler may create a segment for many things. Like it can create a segment for the program itself. It can create the segment for all the global variables. It create a segment for the heap, create the segment for the stacks or for the library, whatever. So you will have a separate segment for different things. Segment for the library, segment for the stack, segment for the heap, etc. So these libraries that are linked during the compilation time may be assigned different segment. Okay, and the loader would take all these segments and assign them a number. Okay, so that's the idea. So the loader will give the number and the compiler will create a segment, will create a segment for each of these things listed above, for the program, for the library, for the stack, for the global variables, for heaps, everything. Okay, then the loader is the one give a number to each segment. Let's say this is the hardware, segmentation hardware. This diagram, it tells you how we are going to access a particular location in a segment. Okay, if you are going to access a particular location, of course, basically remember that in the last chapter even we say logical address, physical address. The address generated by the CPU, you call it logical address. The address, you see it in the memory, in memory, physical memory, that's called the physical address. Okay. So the logical address is the one generated by the CPU. So CPU generates a logical address. It contains two things. What are the two things is segment number plus an offset. Remember. Okay. Just a second. Is it audible now? I hope it's audible. Just a second, because it's still connecting. Just hold on a minute. Okay, hopefully you can able to hear properly. Yeah, that's good. Because I couldn't because able to see. As you see here in the slide, the CPU generates the logical address which contains two parts. It's here. CPU generates the logical address which contains the, can you see in this one, S comma D. S is the segment number. Okay, and D is the offset. Okay, offset means a location inside the segment, a part, or you can say that it is an address inside, something like that, a part in the segment, which is called offset. Offset into that segment. Okay, then so segment number, here it is. S means segment number, D means offset. Okay, so CPU generates a logical address. It contains these two things. So now how it is going to be mapped? How the hardware maps the logical address to the physical address. In the last chapter, I told you there is a unit inside the processor which we call it MMU, memory management unit. That is the one maps the logical address to the physical address. Am I right? So that's the process we are seeing here. How are we going to map the logical address to the physical address? Okay, so S dot D. S contains the segment number. So what do you do? So here it is. So this S, it's telling the segment number. Fine. But I need to have some kind of checking before I map it to the physical address. What is the checking? Can you see here? Here I'm checking something. What I am checking is this the offset valid or not? If it is not valid, you will end up with a trap. Okay, we have a trap to the operating system if the offset is not valid. How do you know the offset is valid or not? Okay, you need to go to the segment table. Here we have a segment table. Can you see here? In the segment table, it contains a collection of something. What is the collection of something? It contains all the segment number along with the size of the segment. See, the segment table contains the size. Size means what? The limit. What do you call here? Limit. Okay. See, the segment table contains, you see here, two things, limit and the base. What do you mean by base? Base means the starting address. Limit means the length of the segment. Okay, the size of the segment, or you can say the length of the segment. So it contains for every segment, okay, segment number 0, the limit and the base. Segment 1, limit and the base. Segment 2, limit and the base. Let's say if it is segment number 5, okay, let's assume that this is 5. This S means 5. So it will have go to the 5, index 5 in the segment table. It contains the base and the limit. So take the limit and compare the limit with the offset. So the offset, either it can be equal to the limit or less than the limit, not equal. So okay, it starts from 0. So it has to be less than the limit. Can you see here? Here you are checking. It has to be, the offset has to be less than the limit. If it is not less than the limit, you have the operating system trap. Trap means it says that you are going beyond the limit. What do you mean by beyond the limit? You are trying to access another location in your memory which belongs to another process, not to this process. Okay, then that is the meaning of it. We call it operating system trap. Okay, if it is perfect, if the offset is less than the limit, then it is a correct address. So what you will do, we will add the offset. Can you see here? We add the offset to the base. You know the base comes from the segment table. You add the offset with the base address, then you will have a address which is the physical address. Go to the address in the memory, physical memory, there is your location. That is your location. So in this way, you are going to convert the logical address to the physical address. So how are you going to convert the logical address to the physical address? Let me repeat one more time. Your logical address is generated by the CPU. It contains two parts. What is the two part? A segment number with the offset. This is the segment number with the offset. First, the MMU checks the offset. Is it less than the limit? How we know the limit? The limit comes from the segment table. So for this particular segment number, go to the segment table, take the limit, and that limit is compared with the offset. If it is not less than the limit, you have the trap to the operating system. In case if the offset is less than the limit, you have the correct correct offset. The offset is correct. In case the offset is correct, you take the base from the segment table. There is the base. Add the base to the offset. You get the proper physical address of your main memory. So this is the way you are going to convert or map the logical address to the physical address. Okay, then. This is the hardware, segmentation hardware. You just try to see that, try to see this, what do you call, diagram? Diagram clearly explains. Okay, I told you the segments are all of variable size. Each segments contains different informations. Okay, this diagram is another example. Okay, example, consider the situation shown in this figure. Here we have 5 segments. The segments, yeah, not this one. Okay, don't think this one. This one, I told you already, this low memory is assigned to the operating system. I'm talking about the other segments. See, segment 0 here and the segment 1 somewhere. Yeah, this is segment 1. I think this is segment 4. This is segment 2. This is segment 3. Don't look into the blue color one. Blue color one, either it talks about it's assigned to the operating system or it's assigned to the process. So I'm not going to bother about these blue color one. Okay then. So let's consider this example shown in this figure. We have 5 segments numbered from 0 to 4. Segment 0, segment 1, 2, 3 and 4. These segments are stored in the physical memory as seen here. So the segment table, as I mentioned in the previous slide, it contains 2 things. For every segment, I have 2 informations in the segment table. What are the 2 informations? Limit and the base. Limit means size of the segment. Base means the starting location in the physical memory. Starting address. Base means starting address. See, here in the, wait a second. So here in this example, segment 0, the limit is 1000. Here it is. Can you see here? Just 1 second. Yeah, here it is. If you want to make it zooming you can do by yourself. When you go to the top left corner, you will see the zoom in, zoom out. Okay. Okay then. So here you may see the segment 0. In the physics, in this side you have this. I can't. Yeah, here it is. I can show you. So this is your physical memory. You I think you can't able to see my cursor now. Yeah, here it is. So this is your physical memory. In the physical memory, you can able to see the 5 segments starting 0 to 4. They are not in the same order. Remember, it's not going to be continuous. I said it's not. It's going to be in in scattered way. So this is your segment 0 and segment 3 is somewhere down here. Segment 2 is beneath and segment 4 is here and segment 1 is at the end. So these are all the 5 segments. Look into the segment table. Segment table contains limit and the base. Limit means the length of the segment, the size of the segment, and base means starting address. See, segment 0, the size is 1000 bytes maybe, and the starting address is 1400. Can you see here? Segment 0 starts 1400. Okay, segment 1, size is 400, very small segment, and the starting address 6300. Can you see here? Segment 1 starts at 6300, size is 400. So 6700 it finishes. You see, you need to add base with the size. You will get the end address. So 6700 is the end. It's for the next segment. It is for the next one. Because you start from 0 to so your segment 1 starts at 6300, ends at 6699, something like that. Okay, not inclusive. 6700, it's not inclusive, exclusive. Okay, it's afterward. Okay, then now same you go for segment 2. See, segment 2, the size is 400 and the base is 4300. Here comes 4003 where the segment 2 starts, and plus 400 you will have the end. You see here. So in this way you have to understand. Let's assume that there is an example here. In this example, let's assume you are planning to access a particular element inside a segment. Okay, let's assume I'm going to access segment 2, a particular location inside the segment 2. Segment 2 is of 400 bytes. So the size of the segment 2 is 400. I want to refer byte 53. Okay, 53 of segment 2. So what do you do? Base plus 53. So this 53 is the offset. I said before in the previous slide, offset and offset. Offset is the one here, 53. Okay. So first you check, is it the 53 less than the limit? Then it is correct offset, or else it is trapped to the operating system. So 53 is less than 400, so it is correct. Now you add the 53 to the base. Segment 2 base is 4300. So when you add 53, it's 4353. It's somewhere here inside in between. You get the idea, somewhere in between. Okay, let's have one more example. Segment 3. Now you go for segment 3. Here it is. I want to refer segment 3. and the byte 852. So segment 3, 852. Okay then. So let's see the comparison. First of all, the offset 852 has to be a valid offset. How do I know valid offset? It has to be less than the limit. Segment 3, the limit is 1100. So it is less than 1100. Now add the offset with the base. So what is your base? 3200 plus your offset, which is 852. So when you add these two, you get 4052. 4052. It's somewhere here. I don't know exactly the location. So that's fine. Okay then. Let's see one more example. I'm going to refer segment 3. Oh, it's gone for me. I hope it is there for you. Okay, let's try to have 1000. The offset is 1222. Can you see 1222 for segment 3? Is it less than the limit or above the limit? It's above the limit, is it? So when it is above the limit, you have a trap to the operating system. You get the idea? So in this way, you can't access the offset 1222 because it is above the limit. Fine. So that's about the example here. Here comes the paging. I told you. There is a solution for the external fragmentation, which is to allow the logical address space to be non-contiguous. To achieve this solution, we have two techniques, segmentation and paging. So now we are going to talk about paging. So here it is. Segmentation permits the address space to be non-contiguous. Okay. So paging is another technique, another memory management scheme that offers this advantage. It's also going to do the same. Okay. But paging avoids external fragmentation and the need for compaction. Okay. It avoids external fragmentation, of course, and there is no need for compaction in paging. Paging doesn't require compaction. But segmentation, we can't say that. Maybe segmentation may need a compaction or it may not avoid external fragmentation totally. Okay, so that's the thing. So what does it mean? So it means paging is more advantageous. It doesn't need compaction and it avoids external fragmentation. So paging is, of course, you can say that a proper, very good solution. Okay. Paging solves the considerable problem of fitting the memory chunks of variable size onto the backing store. Okay, so how we can do that, we will see in the upcoming slides. So because of all these advantages, paging in its various form is used in most operating systems. Remember, paging is the technique, it's used in majority of the operating system, even though in mainframes, even though in smartphones. Okay, so these things you need to be remember. What are the advantages? You just keep it in mind because paging doesn't require a compaction and paging avoids the external fragmentation. Can you get the idea? So the very fundamental method for implementing the paging. So how are we going to implement paging is very simple. Remember, you have two types of memory, is it? Which is logical memory and the physical memory, is it? Logical memory contains the logical address and the physical memory is the one having the physical addresses, is it? So remember two things, logical memory, physical memory. So here you are going to break these memory into pieces or blocks. You can't say pieces, blocks. Okay, you're going to divide the logical memory into blocks, also the physical memory into blocks. So both are all of same same size. Remember, even logical memory, even physical memory, they are going to be of same size. Okay. ಇಲ್ಲ. Okay. Okay. So now, when you say logical memory is divided into blocks, and also physical memory is also divided into blocks. Remember, if you divide the logical memory into blocks, like 5 blocks, so each block size is very similar to the size of the physical memory. Okay, they are of the same size. Each block of the logical memory is of same size of the block of the physical memory. But we are going to refer by different names. I'm not going to use the same name. It will be confusing. So we will be referring with the same names. What is the names we are going to have? Here it is. You see here, uh, when you are dividing your logical memory, you call it as pages. So when you're dividing your physical memory, you call them as frames. But remember, the name is different, but the size is going to be the same. So what is the size of the frame? Each frame size is equal to the each page size. Page means in physical memory. Sorry, page is your logical memory. Frame is your physical memory. Okay, to get my point, what I'm trying to say is, see, this is your logical memory. I say logical memory. So you divide into certain blocks. Remember, equal sized blocks. And this is your physical memory. Let's say I say PH, physical memory. Okay. So you also divide it into same size. I'm sorry, same size. Okay. So the size of this block are going to be of same size. Like 5 bytes, 5 bytes, 5 bytes. Okay, and this is also the same thing. 5 bytes, 5 bytes, 5 bytes. You get the idea? It's going to be of the same size, and I'm going to call the logical memory block. This one I'm going to call it as a pages. So this is the one I say page. So each block is called page. And here in the physical memory, each block is going to be called as frame. So this is the idea. Each block is going to be called as a frame. Here each block is going to be of a page. Okay. Remember in the previous thing we talked about swapping. When there is no space in the physical memory, we can take a process and swap out a process to a backing store and swap in the new process to the physical memory. Do you remember the backing store we discussed before? So the backing store is divided into fixed size blocks, same size of the memory frame. Okay, so everything is divided into blocks that is of the same size. Remember this point. Okay, this is the idea of your paging hardware. The same thing, the CPU generates an address which is called a logical address. It's going to contain two things. One is the number and the offset, is it? So here, the logical address is having two things, which is page number and the offset. So this time, page number. It's not segment number. Now we are talking about paging. So the logical address contains two things, which is okay. This address, logical address generated by the CPU. Can you see here? It's written here P and D. P is the page number. D is the displacement. We call it offset. You know, sometimes they call displacement, they call offset. Can you see here? It's offset. Okay, then. So page number refers an entry in the page table. Can you see here? This is not a segment table anymore. It's a page table. So page table contains certain details. What details it contains? It contains the frame number. Can you see here? page table contains F. F means what? Frame number. So here, take the frame. Okay, for example, the page number is 0. Okay, so go to the page table, go to the index 0, you will have the frame number. Let's say the frame number is 4. So take the 4 and take this offset. So frame number is 4. Sorry, frame number is 4 and the offset is something. So 4 and the offset will give you the physical address. So that's your physical address. Can you see how the conversion works here? Logical address and to the physical address. So logical address contains the page number and the offset. What are you going to do is go to the page table, go to the entry in the page table. Let's say the page number is 0, go to the entry 0 in the page table and it contains the frame number. The frame number. When you join these two, the frame number and the displacement, when you join these two, you will get the physical address. Okay, so this is the idea of paging hardware. Okay. Let's go ahead with one simple, some more other examples. How does it work? Here is one very good example. Can you see here? Your logical memory contains how many pages here? Page 0, page 1, page 2, page 3. So 4 pages are here. So this is 4 pages. Let's see the physical memory. Don't think that if logical memory contains 4 pages, physical memory also contains 4 pages. No. It's not like that. I say we have blocks, is it? Pages here, frames here. The size is the same. Number of pages is not same with number of frame. Don't expect that. From this example, I have 4 pages here. But I have 1, 2, 3, 4, 5, 6, 7, 8 pages here. It doesn't matter. It's not a problem. Okay, then it doesn't matter that you need to have same number of, your 4 page means here 4 frames. No, you can't have it. Your memory is not of the same size. Logical memory and physical memory, they are not same size. Okay, but the size of the page is same with the size of the frame. Okay, if the page size is 5 word or 5 KB and the frame size also 5 KB kilobyte, for example, I don't know. Okay, so this is the idea. So let's see this example in this slide. You have how many pages? 4 pages here. Here 8 frames in this physical memory. Okay. Let's say if you are planning to refer a page, okay, then if you are planning to refer, for example, my physical address, okay, sorry, not the physical address, logical address. Okay, let's consider the logical address, which is like 2 and so this is 2, 5, something. I'm putting it in a decimal. This is 2, by the way. It doesn't look like a 2. I write it here. It's a 2. 2 and 5. What is the 2 here? 2 is the page number. 5 is the offset. Okay. Page number is, this is 2. By the way, it looks like a 1. Hopefully this is looks like 2. Okay, then it doesn't matter. This 2 is the page number, is it? So this is the address generated by the CPU. 2, 5 is the address, which is the logical address. So what do you do? Your P is what? Page number is what? 2. And the displacement is what? 5. So go to the 2, entry 2 in the page table. So in the page table, do you have an index 2? Yeah, I have an index 2. And what is the frame number it contains? It contains a frame number 3. Do you get the idea? So my physical address is 3 and the 5 is the physical address. So what does it mean? 3 is the frame number. See, can you see here 3 is the frame number? And inside the frame, 5th byte or 5th location is the is the corresponding address of this corresponding logical address. Do you get the idea? So this is the way you are going to convert or translate your logical address to the physical address. Okay. Can you see here? Page 2. So page 2 means go to the page table. The 2 contains the frame number. 3 is the corresponding frame number. Can you see here? So 3, this is the frame number. So this frame 3 contains page 2. Okay, go to the frame 7. Frame 7 contains page 3. See page 3. Page 3 is in frame 7. Page 0 is in frame 1. Page 0 is frame 1. Are you able to see this? But inside which location? In this page, in this frame, which location? Which location means which byte I am referring. That depends on the offset. That depends on this offset. This is the one I was telling. Okay then. So that depends on the offset. Fine. So this is about the comparing or matching the logical address to the physical address. So here you have in paging, you have the page table. Page table contains the frame number for each entry. Okay, frame number of each page. Okay, that's the idea. Here they can you see from here, this is also important, which is like this one. Let's assume the address space of the logical address space and also for the physical address space. Let's assume that your logical address space is 2 power m. Let's say m is 4, 2 power m is 16. Okay, and the page size is 2 power n bytes. Okay, in the logical address, the page is of 2 power n bytes. Okay, the size of the page. 2 power n means, let's say n is equal to 3. So 2 power 3 is 8 byte. Okay, then, so 8 byte is the page size. And the logical address space is 2 power m. Remember, m is the bigger one. M is bigger than the page size. Okay. So the higher order bytes contain the page number. Higher order byte means m minus n contains the page number, and the lower n order byte contain the offset n order number. Okay, for example, let me give an example. This one, don't worry about the address space. Ignore the address space. Let's consider the page size. Is it? I say here, page size is 2 power n. Let's assume your n is equal to 3. Simple example, let's consider 3. So, if n is equal to 3, what is your 2 power n? 2 power 3. Okay, so let's assume that your n is equal to, wait a second. Your n is equal to 3. So what is this? I'm talking about the page size. Okay. So your 2 power n, which is 2 power 3, is equal to, do you remember, 8. So 2 power 3 is going to be 8 bytes. So this is of bytes. So when I say 8 bytes, what this 8 talks about, that is the page size. Mean to say I can have 8 bytes in that page. That's the idea of 8. Okay, so what is this logical? Okay, so this 8 is the page size. So here n here refers to 3, n is 3 still. This is 2 power n is 8. Okay, for example, 8 means what? It starts from 0 to 7. Okay, so 3 bits are required to have the 8 to point the 8 locations. What does it mean is, can you see here, 3 bits. So it starts from 000 and then 001. This is for the 1 and etc, etc, etc. You go ahead until 111. What is this 111? Decimal equivalent of 111 is 7. What is the decimal equivalent of 0? It's 0. So I can refer, you get my point, I can refer 8 bytes using the address 3. Where the 3 comes from? 3 comes from the n value. So 3 bits are required to refer the 8 bytes address bits. This is the number of address bits. So 3 bits are going to refer the 8 bytes. So 000 refers the byte 1, the first byte. Okay, and 001 refers the next byte. Okay, and 111 refers the last byte. Okay, its byte starts from 0 to 7. Do you get my point? So this bit 000, this is the offset. I am referring the offset. This is the offset I am telling you. If I say offset is 111, I am referring the last element in page. For example, page is let's say page is 3. Okay, page is 3 means where is it? It is in frame 7. So in frame 7, the offset is 111. So I am referring the last byte in this frame. You able to understand my point here? Is it clear now? What is this offset? What is this page number, etc., etc. Okay, so 3 bits. Why I am saying 3 bits? My n value is 3. So 3 bits are required to address. So these are the address bits. So these are the number of address bits to refer a frame, elements of the frame or bytes inside the frame. So these are the address bit. N here represents the address bit. And then M they represents the logical address space. Okay, size of the logical address space is 2 power m. So if I say m is equal to 16, so let's say 2 power 16 is the logical address space, something like that. This is the way I would like to give an example for this. I hope you understand this n, m, and then the number of bits, etc., etc. Fine. I'll give a small exercise for this also. When I put the exercises, I will make an exercise for this also. Fine. So this is about the paging model of the logical and physical. There is one other example given. This is too detailed example. If you see this example, it will be very clear. Here they gave an example also. What is the value of n? What is the value of m? Everything. So it will be easy for you. Let's say your n is equal to 2. 2 power n is what? So let's say your n is equal to 2. So 2 power n is 4. So let me write it. 2 power 2 is equal to 4. Okay, and m value is 4. It's written here, m value is 4. So let's remember this, m value is 4. So what does it mean? 2 power 4 is 16. Okay, so 2 power 4 is going to be 16. Fine. Let me keep that aside. So main concept is, remember, what is the 16 here? 16 is the logical address space, this one. What does it mean, logical address space? Number of bytes in the logical memory. That is 16. 2 power m is 16. So 16 is the size of your logical memory. So the size of your logical memory is 16 bytes. That's the idea. So what is this n equal to 2? 2 power 2 equal to 4. That is the block size. So the block size is 4 byte. Can you see the block size? Every block size is 4 byte. It contains m, n, o, p, 4 bytes. I, j, k, 4 bytes. Can you see that? Block size. Even the frame. I told you. The frame size is equivalent to the page size. If I say page size is 2 power 2, frame size is also 2 power 2. Can you see here? Also 4 byte. Okay, the size. How to check? You see the address starts from 4 until 8, then 12. So each block here in the physical memory is 4 bytes. Fine. So that's the idea here. So when you have the logical address space when you have the logical address, I told you the higher order by bits, lower order bits, I mentioned how many bits. So here two bits, n bits for the offset, m minus n for the number. Okay, page number. So n bit means 2 bits is for the offset. Okay, and m minus n. Minus 2 is another 2 bits to refer the page number. The previous slide I mentioned that address, logical address. So this is the idea. Okay, let's see how does it work. Remember all those things. Now we will see how does it work. Let's assume that if you have a logical address 0, what does it mean 0? Everything is 0. Page number is 0, offset is 0. So go to the page number 0. Here it is, page number 0. Where is the page? Page 0 is in the frame 5. Where is the frame 5? So this is, wait a minute, frame 0, frame 1, frame 2, frame 3, frame 4, and this is frame 5. Can you get the idea? If the number is not written here, you write by yourself. Page number and the frame number starts from 0. So let's come back to the point. Assume that your logical address is 0. You have a logical address for the number, page number, 2 for the what do you call, the offset. So this is for the page number, this is for the offset. I told you 2 bits for the offset, 4 minus 2 bits for the page number. So this one refers the page number. This one refers the offset. You call it displacement. So this is the page number. So page number is 0. So where is 0? Here in the page table, go to the 0 entry which contains the frame 5. In your physical memory, frame 5 is here. And what is the offset? 0 again. So this 0 is the starting location. You know the 0, here you have the 0 here. See, this is 0th bit. This is 0th bit. This is so bit 1. Sorry, byte 1, byte 0, byte 2, byte 3. You get the idea? So 0, displacement 0 means 0th byte is A. So now I'm referring the location for A. Okay, this is the idea. And now can we see one more example? How do you refer? Here we don't have to count like 0, 1, 2, 3, 4, 5. Can you see here the frame? I say 0, 1, 2, 3. You don't have to count by your manually. We have a technique to count it. Okay, let's see the idea. Let's assume one other example or the same example. How do you know the frame number? Okay, let's see that. One more same example, just a second. Your logical address, it contains 0. 0 means 2 bits for the offset, 4 minus 2 bits for the page number. So my page number is 0. So 0 is here. Page table, where is the 0? It's here. Okay, and the page number, or page table contains the frame number 5. What it contains? It contains 5. What is 2 power 2? In the size of each frame, each page is 4. So when you multiply the 4 and 5, you get 20. So that 20 is where your page resides. So that's my page. This is one example. Let's go to another example. Let's see one more. Let's assume that your logical address is 4. What do you mean by 4? 1, 0, 0. So the last 2 bits for the offset and the remaining bits for the page number. So what is this page number? It talks about 1. So this is your page number 1. So go to 1 in the page table. What it contains? It contains a 6 if I'm not mistaken. See 6 here. So you multiply the 6 with the size of your page in size of the frame, which is 24. So 24 where your frame. This is your frame. Okay, do you see the 24? In that frame, that location, 24 is the address. From that location, your page starts. Okay, for 4 bytes. Size of that page is 4 byte. Okay. You get my point? Your how are you going to map your logical address to the physical address? You can even do the same thing. Here there is a question. Logical address 13. This one you can do by yourself if you want. Logical address 13. So you can write the 13 and break into page number and the offset, and you try to try to map to the corresponding byte in the physical memory. You can do that. You try, and then homework maybe. You want to try it now. You want to try it now? If you want to try, first you need to know the binary equivalent of 13. Tell me what is the binary equivalent of 13? Then we can try it. Because the logical address is 13. So 13, what is the binary equivalent of 13? Anybody? Are you all here, everyone? Okay, here I'm now referring this one, the last part. Let me. Okay, no problem. Here, let me explain one more time, because I gave an example of how are you going to map the logical address 0 to the physical address, and I gave an example of logical address 3. Sorry, 4. I mapped the logical address and I explained already. Now I want to map the logical address 13. I want to map the logical address 13. So if you want to do that calculation, how to map that to the physical address, first of all you need to know binary equivalent of 13. What is binary number of 13? Decimal is 13. What's binary? Any idea? Conversion? You already studied it in digital logic design. Is it? No one knows the binary equivalent for 13. We are in operating system. What's that? Bits, the binary bits I'm asking. Is it that complicated question? Easily you can fix it, is it? 4-bit representation of 13. What happened? 1011. Super. Yeah, that's good. Thank you so much. So 1011. I told you last two bits, the least significant bit, which is 01, is for the offset. And remaining 11 is for the page number. What do you mean by 11? Do you get the idea? 11 is 3. Am I right? Is it clear? Okay. 11 means what? 3 here. It refers page 3. Yes, that's good. So it refers page 3. Go to page, sorry, where is it? Yeah, here it is. Go to the page table. Do you have an entry for 3? Yeah, there is an entry for 3. It contains the frame number. What is the frame number? 2. So multiply 2 with 4, you will get the physical address. So what do you get? 8. So this is the physical address 8. What is the offset? Offset is 0, 1. 0, 1, 0. Are you able to see it? It got, I think it got disconnected, I guess. Now, can you able to see? I hope so. Yeah, I hope so. That's good. So 2 into 4, which is 8. So 8 is the, here it is. 8 is the physical address of that particular page. That's the physical address. But I'm not stopping here. End. You have the offset 1. You get the idea? So 8 plus 1 is 9. So 9 is the physical address I want. What I want from this logical address is the 9. 9 is the physical. You add them together. What you get when you multiply 2 into 4, you get 8. Add with this offset. Add the 8 with the offset, you get the final physical address, which is 9. Do you get the idea? So the final physical address, what I get is 9. How do I get? First of all, you need to know the logical address. That is 13. So 13 is 1101. So last 2 bits is talking about offset. First 2 bit is talking about the page number. This 3. Go to the page table 3. 3 has a frame number. Just 2. So 2 multiplied by 4 is 8. 8 plus the offset is the final physical address. That's it. Is it clear with you all? You don't stop into multiplication, you add with your offset. Okay, so that's the thing you need to remember whenever you are discussing the paging technique. And you need to remember the displacement and how many bits for the offset, how many bits for the page number, what is the logical address space, what is the page size, so that only you can able to identify. Can you get the idea? So this is about the example. Just a second. Okay. We will still continue. We still have time. If I'm not mistaken. Maybe we'll continue with one or two more slides and then we will continue in the next class. Okay, here, one other thing. We can have a discussion here. There is a small problem with the aging. I told you in the beginning, aging avoids external fragmentation and there is no necessary for compaction. These are the advantages I told you for aging. But in segmentation, we can't say it totally avoids the external fragmentation and it may need compaction. So that is the reason paging is highly recommended and many operating system uses these days uses paging. Even the mainframe, even our smartphone, they are all using the paging technique only. Okay then, even though I say no external fragmentation, here it is. There is no external fragmentation, but they've got some problem. What does it mean? You may have some internal fragmentation. What do you mean by internal fragmentation is you assign a block to a process, but the process is not utilizing that whole block. For example, I assign a 10 KB block to a process. Maybe the process is using only 2 KB and the remaining 8 KBs are wasted. Gave a block which is big enough for the process. So it's not utilizing the whole block. That is internal fragmentation. wastage of space inside the allotted memory block. That is what you call internal fragmentation. So paging suffers from internal fragmentation. One example is given here. Let's assume that this is your size of the page. Each page is of 2048 byte, which means 2 KB. Okay, this is the correct number of kilobyte, 2 kilobyte. Okay, then it doesn't matter. You just see it in the bytes. That's enough. Your page size is one page size is 2048 byte. Assume that we have logical memory has many pages. Doesn't matter. For example, a process comes and the size of the process is 72,766. What does that mean? The size of the process is 72,766. When you divide that by the page size, which is 2048 byte, when you divide these two, you will get how many pages I want. So I want 45 pages. You divide, you will get this number. Oh, sorry, 2048. Oh, okay, this way. So when you divide, you get like this. Okay. Plus, not only 45, there is some more byte we have. So 35 pages plus 1086 bytes. So I need 35 whole page plus I need 1086 bytes. I will get this one. So for 35 plus 1086, so what we will do, the operating system will assign 36 pages. Among the 36 page, 35 pages are fully occupied, but the last page, the 36th page, the size of the page is what? 2048. But I'm going to use only this many bytes, 1086 bytes. I mean to say 900, here it is. 946 bytes are not used by the process. Process did not use those bytes. I need to have a page for 1086. So we give a one page, which is 2048. It is using, the process use only 1086. The remaining 962 bytes are free. That means it's internal fragmentation. Okay. Let's assume that if a process needs a page for even one byte, we have to allocate that one. Even for one byte, we allocate a page. No matter we say that this is only one byte, we are not going to assign a page. No, we can't say that. So internal fragmentation occurs. So paging suffers from internal fragmentation. Remember this point? Yeah. Let's move on to some more idea of paging. As I mentioned, that the page size depends on the architecture. Okay, so it's like kind of going to be between 4 KB to 8 KB. This is the typically the size of the pages in certain computer architecture. It depends on the architecture, by the way. Okay. It's sometimes in some other computer architecture, the page size may be more than the 4 GB or sorry 4 KB or 8 KB. Remember, the point page size and the frame size are going to be the same. Okay, but how many pages are in the logical memory? How many pages are in the frames in the physical memory may not be the same. Okay, so that thing you need to remember in mind. And one more thing is process size is independent of the page size. If this situation occurs, then you will have the internal fragmentation. Okay. What does it mean process size is independent of the page size? Let's assume the process is bigger than the number of pages. Like assume that you have page, I have 5 page. Sorry. let's assume I have 5 page and each page is of, sorry, I have 5 page and each page is of size maybe 4 KB. So what does it mean? One page 4 KB. So 5 page 20 KB. So I can have 20 KB of process. Let's assume you have a process. Let's say P is the process. The size of the process is 21 KB. What is this? This page size is not independent of the frame, process size. So what will happen if you want to assign the pages to this process 21, you won't be assigning 5 pages. You have to assign 6 pages. 5 pages for the 20 and you still have 1 KB. For 1 KB you need to assign a page. So 6th page will be assigned to the last pending 1 KB data. Do you get the idea what I am trying to say here? So your process size, this is process by the way, your process size is 21 KB. Assume you have pages with 444 KB. So you assign 5 pages, it will be full, but you still have 1 KB data to be assigned to a page. So 6th page will get 1 KB data. So what about the remaining space will be wasted? Okay. Man, the page size is 4 KB. You just assign 1 KB only, the pending 1 KB data. So the 3 KB is wasted. So that's what you call internal fragmentation. When you will get internal fragmentation, here, if the process size is independent of the frame size, you will get the internal fragmentation. This example we already discussed in the last I think slide. Okay, and one more point you have to remember that it doesn't matter that always the page size will be of same size. Like here in this example, I said, for example, each page of 4 KB. So here, each page is of 4 KB. This is what I said here, is it? Some architecture, they support variable sized pages. So one page will have 4 KB, another page will have 5 KB. Okay, something like that. That is also possible. So let's assume you have a process that needs execution, that's ready for execution. I told you when a process has to be executed, it has to be loaded onto the physical memory, which is the main memory. If a process has to be loaded onto the physical memory, you know already, this is the physical memory, which is okay, this is not the physical, this is still the logical memory. Okay, you in the previous slides you saw a picture of the physical memory where it is divided into frames, many frames. Okay, so the operating system has to know that how many frames are totally in the physical memory and which frames were already allotted to process and which frames are available for the new coming process. So these details has to be available so that the OS can assign a page to a available frame. You get my point. So this is the way. So let's assume here in this diagram you can see some pictures. Okay, can you see this? This is the list of the frames, three frames. Here in this, just concentrate on here. So this is talking about frame list. Like frame number 14. Here, can you see here? Frame number 14, 13, 18, 20, etc., etc., whatever is it. So those are the frames in the physical memory. They are all free. Okay, so here, this is your physical memory where the gray color shaded blocks that are the free. You see the blue color shaded blocks, they are the occupied ones. They are not free. They are assigned to a process. Okay, so here page 16 is blue color. So that means it's assigned to a process. Even 17, even 19, even 21, they were assigned to certain process. Okay. Now, so how many blocks are there? You can see from this detail. you have like a few 1, 2, 3, 4, 5, 6, 7, 8, 9 blocks. Among the 9, 5 are free and 4 were occupied. Okay then, so something you just assume in this way. And this can you see on the top here you have the free frame list. In the free frame list, when a process arrives, assume that there is a process arrives, and where the process will be stored to the which frame, it goes to which frame. Do you get my point? So let's assume that here is the process. Assume a new process comes. Okay, this is your new process. I told process is broken into certain. Wait a second. Here, this is a new process coming to be stored onto the physical memory. So the new process is broken into certain number of pages. Like how many pages it has? 1, 2, 3, 4 pages. Okay, so it's in page 0, it is in page 1, page 2, page 3. So where these pages has to be assigned, can you see here in this table? Page 0 is in 14, frame 14. Here it is, frame 14. Page 1 in frame 13. Can you see here? You can see from the page table. This is the page table. Page table is containing the entries in the page table contains the frame number of the corresponding page number. So if page number is 0, frame number is 14. Page number is 1, frame number is 13. Can you see here? In this way, you assigned the pages to the frame. So 13 is occupied, 14, 16, 18 and 20 is occupied. So from this free frame list, 4 frames were already occupied. So one pending free is only 15 is now free. Okay then. So this is the way. Before allocation, how the list looks like. And after allocation, how the free frame list looks like. Can you see that one? Can you relate to the page table entries now? I guess you now understand. Am I right? So whenever the frame is allotted, the page table entry is updated. Remember that point. Page table entry is updated. This one. Okay. So the operating system, this was the one I was telling before. The operating system should be aware of certain things. What are the certain details? It needs to know which frames were allocated before, which frames are available free now, totally how many frames are there, etc. etc. So it needs to know many details. So where are these details? These details are kept in a table called frame table. Okay, so this frame table has one entry for each physical frame. So similar to the page table, frame table also has each entry for each frame. So entry for, in the table, there is an index. Index tells you the number, page number or frame number, something like that. Okay then. So this frame table contains those details. Let's see how does it look like. So there are many different ways of having this details. Okay, so each operating system has its own method for storing the page tables. It depends on the operating system itself. Some allocate a page table for each process. A pointer to the page table is stored with the other register values. Let's say, for example, instruction counter or whatever is it, something like that. This is a kind of a technique used by some operating system. Mean to say allocate a page table for each process. Okay, then for each process you have a page table. Okay, one process contains one page table. Another process will have another page table. So there is a pointer to the page table. There is this pointer. The pointer is stored in a register. Okay. Okay, it's stored with other registers, other register values. Okay then. So the implementation, the hardware implementation of the page table, it can be done in different ways, several ways. Okay, one simple way is implementing the page table as a dedicated register. So this is one simple way. I'm not telling that this is the one and only way. This is the very easy way of storing the page table entry as set of registers. So the use of the register for the page table, that is satisfactory when if the page table is reasonably small. You know, if for example, if a process comes in and that process size is of 20 KB, let's assume that, okay, and my page size is, for example, 2 KB. One page size is 2 KB. So I will have a page table entry. How many pages I need? My size is, my process is of 20 KB and each page is of 2 KB. So I need 10 pages. So your page table will contain 10 entries. The index will start from 0, 1, 2, 3, etc. And the process is divided into certain pages, and this is your page table entry. Okay, so in case if you want to use registers, then suppose to be you need to have a small process. Then only you will have small number of pages. Okay, so registers will keep that detail, the page frame number of each process. Can you get the idea? Because remember, there are not many registers. Only few registers are available. Registers are not that many. In any operating system, sorry, in any architecture, do not expect you will have a plenty of registers. Okay, there are registers only. We already studied MIPS. Do you remember in architecture we studied MIPS? Hardly how many registers we had? 32 registers. That's it. Okay, so maybe it goes up to 64 register. You won't have like a big number of registers. Okay, so if your process is small, okay, you can make use of registers. Okay, then for page table. Okay, for page table entries, you can have like this entry goes to one register. Another entry is saved in another register. So in this example, 20 divided by 2, I need 10 pages. So the 10 registers are needed to keep the frame number of each page. You get the idea? 10 registers are needed, something like that. Okay, so remember this point when to use registers. Use of the, okay, for example, in case of most recent computer, latest computer or the new trend of computers, allowing the page table to be of very large. I mean to say that maybe 1 million entries, page table with those many entries. If you have 1 million entry in a page table, obviously you can't use register. I told you there is only few number of registers. Okay, so for this type of machine, it's not possible to have registers. No way we can use it. As I mentioned before, there are not like this many number of registers. Instead, you keep the page table in main memory and page table base register, we call it PTBR. There is a register called page table base register. It points to the page table. Where is it? It's in the memory. Okay, so this is the good idea. So keep the page table inside your physical memory, and that's your main memory. You call it physical memory, and you keep one register. Make use of one register. That register contains it's a pointer to the page table entry in the main memory. What do you mean by pointer? It's the containing the address of the main memory where your page table starts in main memory. That's the idea of the page table base register. Okay. Of course, in case if you are changing the page table, it requires changing only the register, which is page table base register. Just change the page table base register. Okay then. But it's not the very kind of very nice idea to have this. It has some issues. This technique also has some issues. This method. What's this problem with this approach? Is the time required to access a user memory location. That is the idea. Okay, so that's the problem with this approach, the time. required to access the location in your main memory. For example, if you want to access a particular location, and we must first index into the page table. Where is the pointer to the page table? It is in the page table base register. And you know that pointer, that is the offset by the page number I. So you take the page table base register content as the offset, and that gives you the address, actual address. Do you get my point? So let's assume that your physical memory, so this is the idea. Let's assume you have the physical memory. So you keep your page table inside the physical memory. So it has the address. Can you get the idea? There is an address, the starting address of this page table. So that address is kept in a register. What is the name of the register? Page table, page table base register. So this address is saved in this page table base register. So this is your physical memory. So physical memory, this is the physical memory. The starting address of the page table is saved in the page table base register. Let's say I want to access an entry inside the page table. So what you need to do is take the content of the page table base register, you add the offset, you will get the actual address in the physical memory. So this whole thing may take certain amount of time. It's not just very simple. It takes more time because you need to take the content of the page table base register, you add the offset, then you will get the actual address in the physical memory. That time, it's a time consuming. That is the problem associated with this approach. Fine. So is there any way to do that? Is there any way to have any other solution? So a solution to this problem is, let's go to next one. Okay. So what is the solution to this problem is, okay, you can use a buffer. Buffer is called translation look-aside buffer. This is a kind of a solution to this issue. You keep one point in mind. Whenever you say buffer or faster storage unit. This is the idea of buffer. Buffer is not a big storage unit. It's a small storage unit, and that will be fast enough to access it. That's the idea of buffer. Okay, so this is a solution. Use a small, fast cache memory. Okay, buffer means you can even consider it as a cache memory. So when you compare register and buffer, register and cache memory, of course, cache memory is faster than register. Remember this point, okay? So whenever you say buffer, you can relate to the buffer. Buffer means it's a cache memory. Okay, so that is faster than the registers. So remember this point. So you can use a special small fast cache memory that you call it as a buffer. What is the proper name? Translation look-aside buffer. It's written here LB. Just a second. Yeah, it's mentioned somewhere here. Yeah, it's here. Can you see here? Translation look-aside buffer. It is a high-speed memory, but it is a small size memory unit. Okay, and it's fast enough. Okay then. So what is going to have this buffer? It's going to have two things. It's going to contain a tag, the key, along with the value. These are the two values. You're going to keep it in the buffer. For example, when associative memory is presented with the item is compared with all the keys simultaneously. For example, if an item is found, the corresponding value field in that buffer, that will be returned. So this type of searching is fast, and the TLB lookup in the modern hardware is part of the instruction pipelining. Don't worry, the pipeline we will discuss in detail in upcoming chapter. Okay, pipelining is really a concept, a big concept. So we will discuss it in the upcoming chapter. For time being, you just understand that it's a kind of a key part in instruction pipelining. There is no performance penalty. What do you mean by penalty? Is a delay. There won't be no extra delay here. Okay then. So your buffer is going to contain a key and a value. And when there is a memory, I want to search a particular location in a memory, you will be searching the set of buffers. Okay, you will have collection of buffers, for example. So how are you going to search? With the key. You need to say the tag. When there is a matching tag found, then the corresponding entry in that the value content will be returned. That value is the one it's going to be used for the actual address. Can you get the idea? So in this way, even the idea is the same. Anyway, you are going to search certain number of buffers. But I told you a few minutes ago, searching a value or accessing an element inside the buffer is faster than registers. So there is no penalty here. Okay. So the translation look-aside buffer is used with page tables in the following way. How are we going to use is, so translation look-aside buffer contains, where is it? Here. Let's assume that your buffer is going to contain only few of the page table entries. Whenever there is a logical address, its page number is sent to the translation look-aside buffer, page number. The key is the page number because you said, you know few minutes ago, the buffer contains a key and the value. Is it? What is the key? Is the page number. Okay. So whenever the logical address is generated, and that address is presented to the buffer. I mean, it's sent to the buffer. So to search which buffer entry contains that page number. So if the page number is found and the corresponding value field is the frame number. So the frame number is immediately available. That is used to access the memory. You get the idea? So this is the way. So buffer contains two things, key and the value. So here it is, key and the value. Key is the one, it's the page number. Value is the one, frame number. Same thing is you are going to store here, but it's faster because buffer is faster than registers. Remember this point. Okay, just we will move on to, in case if a page number is found, then okay, you take the value, that's the frame number, because buffer contains two things, a key and a value. Remember. So what the buffer contains? So buffer contains, for example, it contains the key and the value. The key is the page number and value is the frame number. Can you get the idea? So it will search the buffer. You have certain list of buffer, not one buffer. Okay, so you will have many entries in the buffer. So you try to search for the page number. If there is a page number found, the corresponding frame number is taken out. Okay, this is the frame number to access the physical memory. Okay then, when the page number is found, then that is called hit. It means found it. But if TLB hit, you call it translation look-aside buffer hit. It's not necessary that always you will have the page number in the buffer. Maybe there may be a miss. Call it translation look-aside buffer miss. Okay then. So when there is a miss, okay, it's there in the here. Okay, here it is. Yeah, you see here, if the page number is not found in the TLB, Translation look aside buffer. If it is not, means the term to represent the situation is TLB miss. What do you mean by TLB miss? It means the page number is not found in the buffer. The page number is found in the buffer, it is called TLB hit. Hit. Okay, you call it hit. It's not written there. You call it a TLB hit. Okay. So let's assume that the page number is not found. What you need to do is you need to make an entry in the buffer. So a new entry is created. So this may be, okay, can you see here? Reference to the page table has to be made. A new entry has to be created. So for the corresponding page number, what is the frame number? You try to obtain it. How can you do? You try to access the memory and try to obtain the data. So add the page number and the frame number to the TLB. Why we are adding it? For further reference, we can able to use the buffer. Do you get the idea? So when there is a miss, TLB miss, you need to find the corresponding page frame number of the page number, make an entry in the buffer. Further reference, the next reference. In case if the buffer is already full, buffer means I told you it is a small memory unit. It's a cache memory. Cache memory is not the big like your main memory. It's bigger than the register. But okay, let's assume that it's bigger than the register, but I can't say that it's bigger than the main memory. It's a small one. Okay. So assume that your TLB is already full of entries. So can you see here? This is the TLB. Wait a second. In this diagram, can you see the TLB? It has how many entries? 1, 2, 3, 4, 5, 6, 7 entries. Let's assume the 7 entries are already full. There's no more free spaces. What you need to do is I want to store some page number and frame number in the TLB. What you need to do is, do you remember last time we had something like you take some entry out of it and put the new entry. So same thing we need to do. That's what we call replacement. So you take an entry from the TLB, you remove it and then put the new entry inside the TLB. This is what we call replacement. Okay, replacement means you replace an entry with the new entry. Okay, that's what you call replacement. There are plenty of technique for replacement. What is the plenty of technique? A lot of techniques, replacement policies. What is this is? Okay, here in this example, how many entries are there in the TLB? 7, I think. This is your TLB, is it? 7 entries are there and it's all full. It's all occupied. I want to put one new entry here, like a page number and the frame number. So here I need to decide which entry I'm going to choose. Do you get my point? Which entry I'm going to choose. I can't, just like that, I can't go with one entry like the first entry. I remove that entry and I add the new entry. No. There should be some technique you have to follow. So which entry has to be removed? Where to put the new entry? There are some techniques. So that is, we have many, we will see them. They are like least recently used. This is one technique. Another one is round robin. Another one is random. Okay. So these are all called replacement policies. Okay, then we will see this techniques kind of after a while. Okay, then in the next topic we will see what are these techniques. But I can even tell you what is this least recently used means. Among these 7 entries in the TLB, which entry was least recently used means recently not used. Okay, which entry is not used recently? Long time ago it was used. Recently the OS doesn't use that entry. So mean to say it's not used for a couple of time. You can remove that entry. That entry can be selected for replacement. That's one thing. And round robin. You already studied round robin in the CPU scheduling. you'll go around, like first time you select the first entry, next time you go for the second, and then third, and then fourth, and the next time you want come back to the 1, 2, 3, 4, something like in a circular way. You go in a circular way. Last time I choose 1. So this time I want to replace means I'm go with the second entry. Next time I want to replace means I'll go with the third entry. That's round robin. And the last one here, it's mentioned random. This is the one, randomly you pick any entry and then you replace it. That's random. Okay, so these are the techniques. There are different techniques available. It depends on the operating system, which technique it is going to use. It depends on the OS only. It's not by us. Okay, so here you can see from this idea, the table, the figure here, it clearly says the idea of the use of TLB. CPU generates the logical address. Remember, the address generated by the CPU is the logical address. What does it contain? Always it contains two things. One is the page number, another one is the displacement, offset. So the page number is searched in the TLB. If there is a hit, then the corresponding frame number is taken out. And then the displacement. When you add these two, you will get the physical address. This is one way. Imagine that there is a TLB miss. There is TLB is not there, then of course TLB you will, then of course if there is a miss means go ahead with the page table. So the page table will contain the frame number. Take the frame number and add the placement, you get the physical address. Can you get the idea? So searching the page table, was the one I was telling in the before. Searching the TLB to take the frame number and go to the memory, access the memory is faster. Searching the page table entry is slower because page table is long enough and the buffer is short enough. Okay. Moreover, where is your page table? You already store the page table in the physical memory only. So you are referring the physical memory. And accessing a big memory takes more time. Do you get my point? So that's the idea of TLB here. Let's move on to, okay, the time calculation. Yeah. The percentage of time the page number of interest is found in the TLB is called hit ratio. I told you hit means you found the entry in the TLB. Cancellation, look aside, buffer. So the percentage of time the page number, of whichever page number I want to find, if I find that time is called percentage of times. Wherever I found my entries in the TLB is called hit ratio. 80% hit ratio means 80% of the time I find it in the TLB, but 20% of the time it's missed in the TLB. That's the meaning of 80% hit ratio. So it's mentioned here. The desired page number is found 80% of the time. Okay. So let's assume that if it takes 100 nanosecond to access a memory, second. Yeah. If it takes 100 nanosecond to access a memory, then a mapped memory access may take 100 nanoseconds when the page is in the TLB. Okay. But in case if there is a TLB miss, in this case it's not there in the TLB, so you have to access the page table. In the previous diagram, I said, okay, you have to access the page table. Where is the page table? I told you page table is in the physical memory. Okay, and what will happen here is you may have extra time, 100 nanosecond to refer the page table, another 100 nanosecond to refer the frame. So 100 plus 100, you may end up with 200 nanosecond. If there is a hit, 100 nanosecond. If there is a TLB miss, it is 200 nanosecond, double the time. I told you already. Okay, having a TLB is faster. The buffer is faster than the memory, something like that. Okay, so you can able to understand from this idea. Let's try to have some calculations. So there is a calculation given in the oh no, the calculation is not given in this slide. That's good. That's good. Okay, but remember this point. Accessing a location, let's assume that if the time it's going to take is 100 nanosecond, then for hit, what will be the time? For miss, what will be the time? You need to remember this. Okay then. Okay, this one you need to remember. In case if it takes 100 nanosecond to access a memory, access the buffer also 100 nanosecond. Okay, to access the buffer, and from the buffer you take the data of the memory, so that's okay. If there is a hit, 100 nanosecond. If there is a miss, then it will be 200 nanosecond, because your page table is also inside the memory and your frame is also inside the memory. So 100 nanosecond to access the memory. So I am accessing two times, one for the page table, one for the frame. So 2 times 100 is 200. Fine. So just remember this type of this type of questions whenever you go through. So you remember these things. Okay then. Now let's move on to the protection, kind of protection of your memory, like memory protection. So protection in the paged environment, how are we going to do is, it's by, you are going to use a bit called protection bit. It going to be with the frame. It's going to be associated with each frame. So memory protection is accomplished by the protection bits. So you are going to have a bit. We call it a protection bit. These bits are kept in the page table. Remember, we already saw page table. Page table contains the frame number, one entry in the page table. Is it? Now we are going to have one more entry. Okay, one more. You will see another column. That column will be called as protection bit column. One column for the frame number, one column for the protection bit. Okay then. So each frame number will have a protection bit. Okay then. So this one bit can define a page to be read, write, or read only, or whatever. So this page can only be read, or can only be written, or can be read, write, whatever. Okay, so that's the idea. So the reference to the memory goes through the page table to find the corresponding frame number. You need to go to the page table, take the frame number, go to the main memory. So this is the way we do until now. So when you are going going through this way, you will be same time. What are you going to do is you take the protection bit, and that can be checked to verify. Let's assume the protection bit says this page can be read only. So I take the protection bit whenever there is a write attempt for read only page. So there is a violation here. You have a hardware trap because there is a violation. The bit says the page is only read only, but there is an attempt to write something onto the page. Can you get the idea? So the page causes, the read only page here causes the hardware trap to the operating system because it's violating the privilege. So this is the idea of the use or purpose of the protection bit. Another additional bit is also associated with the page table. One more bit is going to be added. What is called that bit called valid invalid bit. That bit is called valid invalid bit. If this valid bit is set to valid, the page is in the process logical address space. and thus valid page, something like that. When this bit is set to invalid, the process is not in the logical address space. So illegal address are trapped. I use the valid invalid bit. Okay then. So you are going to have two things. A protection bit is there. The protection bit tells the OS what type of privilege is given to the page, like read write or read write or whatever. If there is an attempt to override the privilege, you will have a hardware trap. That attempt causes hardware trap to the operating system. And along with that, we have additional bit that's called valid invalid bit. Remember that also. The next slide, I guess you see that page table entry, if I'm not mistaken. Valid invalid bit. Okay, where is it? Here I can explain. Here I can explain when it is valid, when it is invalid. Let's see, this is your process. Logical address space. This is your physical address space. Okay then. And this is your page table. Okay, let's see. Now, assume that this wait a second. Let's start from here. So let's see the logical address space. What are the pages you have? Page 0, page 1, page 2, page 3, page 4, page 5. So how many pages? Starting from 0 to 5. Okay. So 0 to 5 is my logical address space. So can you see the entry in the page table? V and I. V means valid bit. I means invalid. So when there is an address in the pages are mapped normally through the page table, is it? Okay. Any attempt to generate an address in the page 6 and 7, you may see invalid. Because there is no such page exist. My page starts from 0 to 5. Can you see? From 0 to 5, it's valid. Any attempt, you will find that valid invalid bit is set to invalid and the computer will trap to the operating system because it's an invalid page reference. There is no such page 6 or 7. You get the idea? So this is about the memory protection in the paging. Okay. So let's move on to shared pages. So what's this shared pages is, you can have some common code and that can be shared. This is an advantage of paging. So mean to say a common code that can be shared. This is very useful in terms of time sharing environment. Let's assume a computer system support 40 users and each of them are executing a text editor like a Word document. They are using Microsoft Word, for example. The text editor consists of the size of the text editor is, let's assume it is 150 KB, and this is for the data space, like for the document or a letter 50 KB. So assume there are 40 users and everybody is using the text editor. Okay, so one user, let's assume this user, this user is using text editor. So how many spaces needed? 150 plus 50 for the document. Is writing a document or is writing a letter in the Word. Another user go with the same thing, like 150. If we open the Word editor, is it Word, Microsoft Word or whatever, and 50 for his document or a letter. So it goes on like 50 users. How many users? 40 users. Okay. When you multiply, you will get, oh my God, you need, can you see here? 8000 KB. Because each one is having, each one need a space, memory, space for them, the document plus the application. A document plus the application. Document plus the application. Application is same overall on the 40 users. It's the same Microsoft Word, but the document may be different. I may be writing a letter. Another user may be writing a document. Another user may be creating a report. So there, the content and the document is different. The 50 is okay, it's not the same. Okay, this 50 is like a different for different user, but this 150 is the same Word app. You get the idea? So in this case, we can have sharing, page sharing. Okay, so in this, the page editor can be of in a page. The word editor or the text editor can be of in a in a page, in a set of pages where the each user can able to share it, like kind of use it, access it. Okay, share the access to the common pages. Okay, so that is the idea of this. Okay, just one thing. So here, just to go through this point also, re-entrant code. What do you mean by re-entrant code? Is non-self-modifying code. What does it mean? It's not going to change during the execution. Okay, so mean to say, Word app, I'm opening a Word app and many people are going to use it. So it's not going to be changed during the time. So many people can use it at the same time. That's re-entrant code. Let's keep this point in mind. Just a few more to go. So let's see the yeah, here is the more detailed diagram. It shows the shared pages. Let's assume there are many processes. Okay, each process. Take the same example of having a word editor to do some documentation. Okay, so let's assume there are many processes. Here in this, maybe process P1, P5. P3, yeah, it's P1 and P3. So let's see, there are the one or two processes. So two processes, for example, process P1 here, process P3 here. Okay. And what is this? It has a copy. Each process has a copy of the register data to hold the data for the process execution, etc., etc. So it has all these details. See here, ED1, ED2, ED3, and data. And here also ED1, ED2, ED3, and the data. Can you get the idea? And there is a process 2 also, I forgot here. There is one more. So totally 3 processes you have. Again, what it has? ED1, ED2, ED3 and the data. Okay, so that data, can you see that data is the one different here. So here you have a process table, sorry, page table for 1, page table for P2, page table for P3. You look into the page table, you will see the shared pages. Can you see page 3? This one, it's not page 3. This is the frame number. Whatever written in the page table, it is the frame number. See, 3, 4, 6. These frames containing the 3 editor, ED1, ED2, ED3, because they are the same editor. So this page table also contains the same frame. This page also contains, the table also contains the same frame, 3, 4, 6, 3, 4, 6. This contains the editor 1, editor 2, editor 3. Can you see here? Frame number 3, frame number 4, frame number 6. But the data, it is in, okay, D1, data 1 is frame 1, data 2, here it comes. Data 3, these are all different. Can you get the idea? So, you're not going to keep 3 copies of the editor 1, editor 2, editor 3. You're just keeping 1 copy in the physical memory. In the physical memory, you just keep 1 copy, ED1, ED2, ED3. So that same frame is shared between the 3 processes. You get the idea? So in this way, you are saving the space. I'm not going to require that big space. Do you remember in the previous slide we calculated 8000 KB is needed? No, now it will be like 2150 KB enough. So you save the space of the physical memory. I hope you understand. Yeah, that's good. So let's move on to the structure of the page table, and with this we can conclude this chapter. So when you say structure of the page table, sorry, I'll go back to one more step ahead. So the structure of the page table, first we are going to talk about hierarchical paging. Hierarchical paging means in the modern or in the latest computer system, it supports a large address space, a logical address space. In that case, page table will of course be large enough. The logical address space large, you are going to have a page table for that logical address space. Your page table will also be bigger. Okay, let's assume one example. Here it is. Consider your logical address space is 32-bit. This is the size of your logical address space. And 32-bit, okay. And if the page size is 4 KB, assume this way. So, a page table may consist up to 1 million entries. Okay, so this is the idea. Let's assume each entry contains a 4 byte and each process may need up to 4 MB of physical address space for that page table alone. Okay, so in this case, we would not want to allocate the page table continuously in the main memory. Of course, we can't do that. Simple is we divide the page table into smaller pieces. Okay, so you are going to divide the page table into smaller pieces. So this is the way we call it two-level paging structure. What is it? Let's see. So you are going to have two-level page table scheme. So what is this two-level is? You may see here outer page table and your the one broken into the second level, the first level and second level page table. Can you see here? This is one level and this is the another level. So it's too simple here. So this page, outer page table contains the whole list of pages. But the inner page table, can you see here, inner page table, it's like consists of um, like multiple tables. See, this is one table. This is another table. This is another table. Multiple tables. So each page, it's going to have a table. A page for the page table. Okay, each page is going to have a table. Okay, so this outer table, it has a few entries, is it? So this each entry points to a table. This entry points to a inner table. This entry points to inner table. And this page table in that entry contains a frame number of the physical memory. You get the idea? So this page table inside the second level contain the physical address. So here how many entries are there? 500 entries are there. And here maybe 600 plus, and here like few. So can you see here? So this contains frame 1, this contains a frame 500. I don't know. I don't know how many frames are inside. But smaller than the outer page table. So you have the outer page table which contains certain pages. Each page contains a page inside. Each entry in the outer page table contains a page table. That table is the one referring the original frame number in the physical memory. So here you have the outer page, and this is the inner page number, and this is the offset. You get the idea? Mean to say the displacement. So logical address, we need to know these things. Okay, we need to, normally what is your logical address? Logical address contains the page number and the offset. Here, it's going to have two page number and the offset. This is the logical address. Logical address contains three entries now. Page 1, page 2, offset. Okay. So because I need the page number for this table, I need the page number for any of this table, I don't know, maybe this or another one, I don't know. So logical address contains three entries: outer page, inner page number, offset. Outer page number, inner page number, offset. Remember this point. This is two level. It's not necessary only two level. We can still go up to like three level or whatever is it. Okay. This is one simple example, two level. So this is the address translation. Can you see here? I told you a few minutes ago, logical address space contains three things: outer page number P1, inner page number P2, and the displacement. Okay then. So it starts from the outer page and then inner page. So this is called forward mapped page table. Okay. So you go to the outer page table, go to the particular entry. Let's say this is the entry. It contains another page number. Okay. So go to that entry here. You get the idea? And it contains the frame number. So in that frame number, what is the offset? Or what is the offset? You add the offset, you will get the corresponding physical address.